Hello, my name is Paddy Hayway, and I'm a postgraduate student working in Professor Justin Walk's group at the University of Oxford. In this presentation, I'm going to be speaking about some work we've undertaken towards understanding the behaviour of tantalum during shock release, particularly regarding the evolution of its temperature, and whether or not that squares with the traditional isentropic picture of shock release. So our work can be summarised as follows. We've performed molecular dynamic simulations of micron-scale tantalum monocrystals that are shock compressed to about a megabar and are subsequently allowed to release back to ambient pressure. We've tracked the temperature evolution of a set of Lagrangian material elements that are equispaced along the length of the crystal, and we've found that their release is markedly non-isentropic, which is to say that they are far hotter than expected. We've attempted to interpret their temperature evolution as coming from a sum of thermoelastic cooling due to expansion, heating due to plastic work, and exchanges of energy with the material microstructure with moderate success. That temperature analysis revealed that it is indeed plastic work heating that is responsible for the elevated temperatures, and that plastic work heating in turn is owed to the considerable strength exhibited by the crystal during shock release. And finally, we performed corroborative shock compression experiments in which we observed the same excessively high release temperature following shock release via the thermal expansion that can be measured in situ using X-ray diffraction. To begin, I thought I'd show a simple animation illustrating in a schematic way what the shock release process involves. So we start by rapidly loading the front surface of our sample in order to generate a shock wave, behind which the material is high density, high pressure, high temperature, high velocity, and so on. That shock wave propagates through the sample in a nice self-similar way until it reaches the rear surface, at which point it encounters a free boundary that is completely unable to support the state of high stress engendered by the shock. Consequently, a rarefaction wave is launched back into the sample that gradually allows it to release back to ambient conditions. Obviously, the conspicuous feature of a release fan is that it gradually broadens with time, unlike a shock, and so the release rate falls as one moves further away from the rear surface. Now, the canonical treatment of shock release treats the process as being isentropic, so that means when the crystal expands back to ambient volume, its temperature evolution is governed exclusively by the thermoelastic effect, which causes the crystal to cool by typically several hundred degrees during release, at a rate dictated by the Nonisentropic parameter. However, that premise, that release is isentropic, is predicated on the notion that the typical strength or flow stress of the material during release, which determines the rate at which plastic work is performed, is negligible compared to the overall pressure scale at which the release is taking place. Now, while that assumption might be reasonable for the kind of millimetre scale targets used in gas gun experiments, where the release rate is slow, we know that in the micron scale targets now routinely used on laser compression platforms, there's simply not a big enough runway, if you like, for the release wave to broaden over, meaning the release rate within these targets can be exceptionally high, and by that I mean in excess of 10 to the 9 inverse seconds. Furthermore, it's now well understood that if you force a crystal to undergo plastic deformation that rapidly, you're going to have to exert shear stresses of order gigapascals to get it to do so. That is going to lead to a large amount of plastic work that will directly heat the crystal. We now also have strong experimental evidence of reversed plasticity during shock release, which can cause some fraction of the huge defect density nucleated on shock to be annihilated, so the energy stored by those dislocations can be partially recovered during shock release and released as heat. So the purpose of the work described in this presentation is to explore the role of plastic work and this defect energy recovery, and to see whether these heating mechanisms can beat thermoelastic cooling. So I'll first talk about the molecular dynamic simulations we performed to that end, which were actually very simple in their design. So we simply take single crystals of tantalum with their 0, 1, 1 direction aligned with the loading axis, Z, or Z rather, and shock compress the crystal to about 100 gigapascals using a constant velocity piston. And obviously we run the simulation long enough that the crystals can be allowed to release. The central focus of the simulations was to track the evolution of a set of Lagrangian material elements as they undergo shock and subsequent release, monitoring their temperature throughout, and to see whether their behaviour could be understood with reference to their strain state, stress state, defect state, and so on. and I'll be focusing on the results for a particular element situated just 0.2 microns from the crystal's rear surface. In this graph, I'm showing the elastic strain state of the element as a function of time, which I think illustrates quite nicely the whole shock release cycle. So we see that the shock wave strikes the element at about 185 picoseconds, which raises the strains along the 3 coordinate axes to about 9%. The element stays compressed for about 60 picoseconds, during which time the shock wave traverses the remaining 200 nanometers of the crystal, breaks out from the rear surface, and then launches a release wave back into the crystal that first encounters the element at about 247 picoseconds. From the graph we can see that the release back to ambient pressure actually takes place in 2 phases. So you see that there's first a period of elastic release, during which the elastic strain along Z rapidly decreases, but the transverse strains remain constant. But within 5 picoseconds, the shear stresses inside the element have built to such level that the crystal yields, plastic flow ensues, and that's evinced by the transverse elastic strains decreasing at about the same rate as the longitudinal elastic strain. If we now overlay the element's temperature evolution, shown by the solid red line, we can actually see some interesting behaviour. So the shock wave first raises the temperature of the crystal from 300 Kelvin to around about 1750 Kelvin. Then, during the elastic release phase, we can see that the crystal starts to cool, which is what is expected because of the thermoelastic effect. However, as soon as plastic flow begins, the temperature of the crystal practically stagnates. So for comparison, I've also plotted the release isentrope emanating from the shock state in the dotted red curve, which clearly parts ways with the actual release path immediately after the point of yielding. So this is indicative of a heating mechanism that is pumping heat back into the crystal as quickly as thermoelastic cooling can remove it. So let's now attempt to interpret the temperature evolution of the material element. So in principle there are 3 source terms. There's the thermoelastic cooling term T.Te, which depends on the Grunheisen parameter gamma and the elastic strain rate d epsilon E by dt. There is the plastic work heating term T.Pw, which depends on the Cauchy stress sigma, the plastic strain rate d epsilon P by dt, and the element's volumetric heat capacity Cv. And then there is the rate of change of energy stored by the microstructure, which is labelled E superscript S. Note that the thermal conduction is completely negligible over the timescales of interest here, i.e. nanoseconds, hence there being no diffusive term in the heat equation. The graph on the right shows once again the measured temperature evolution during shock release in the solid red curve, and also the release isentrope, which is basically just obtained by integrating up the thermoelastic cooling term only. We can now overlay the solution to the heat equation obtained when one switches on plastic work heating, and actually you can see that plastic work heating alone can account pretty convincingly for the unexpectedly high release temperature. However, it's clear that the shape of the release path leaves something to be desired. It departs way too quickly from the isentrope and is a bit too flat at late times. However, if we also switch on the defect term, the agreement becomes much better. Basically, the reason the temperature drifts up slowly at late times is due to thermal energy being recovered from the gradually diminishing dislocation network that's created by the shock. Now, there is admittedly a rather conspicuous difference between the observed and predicted release paths. The 2 curves seem to drift apart between around 255 and 290 picoseconds. We think this is owed to the fact that the release rate is essentially so rapid that our heat equation, which is based on the tacit assumption that the conditions of thermodynamic equilibrium apply, is starting to break down. And this is something that we will be investigating further. However, we think the agreement is sufficiently good that we can conclude confidently that it is indeed plastic work heating that is primarily responsible for the unexpectedly high release temperature predicted by these MD simulations. So the simulations predict the crystal is hot, and we think we understand why that is. The next natural question is, can you actually see this heating in experiments? Well, we believe the answer to that question is yes. So the experiment in question was conducted at the matter in extreme conditions end station of LCLS, and the configuration is a pretty standard one. Our targets comprise 6 micron thick polycrystalline tantalum foils with a 50 micron polyimide ablation on their front surface that are shock compressed to about 1 megabar with a set of high power pulsed optical lasers. The texture of the foils is such that each grain has its 0-1-1 direction closely aligned with the loading axis, and the foils are probed with the X-ray free electron laser as they are releasing, and the resultant diffraction patterns are then recorded on a set of Slack Cornell pixel array detectors. Now, the inset in the top right shows some archetypal diffraction data obtained during shock release. We see first that there are strong diffraction peaks at high values of scattering angle 2 theta, which comes from that fraction of the foil that is yet to release. We then see a continuous streak of diffraction intensity moving back towards lower Bragg angles. This of course comes from the gamut of density states present in the release fan. And finally, we also find strong diffraction peaks at relatively low scattering angles that comes from the fully released material. Now, it so happens that the focusing of the X-ray beam provided by the beryllium lenses is somewhat imperfect, and we get what's called a halo around the X-FEL beam proper, which falls outside the optical drive spot and thus always diffracts from uncompressed material. This gives rise to constant diffraction peaks whose position tells us the ambient density of the material. Conspicuously, the scattering angle of the released material is lower even than that of the ambient material. So that means the shock-released crystal is less dense than it was before it was shocked. Now, since the released material is, by definition, no longer subjected to stress, that expansion has to be interpreted as thermal expansion. That is, the crystal has overall expanded because it is hot. Thus, if we know the thermal expansion coefficient of tantalum, we can convert the increase in volume measured directly from the diffraction into a release temperature. So in this last figure, I'm showing in the pressure temperature plane the Hugonio, i.e. the locus of shock states, and the locus of corresponding isentropic release states as a function of shock pressure. I'm also showing where the ambient melt temperature of tantalum falls, which is about 3300 Kelvin, for reasons we'll come to in just a second. I now show the release temperature we infer as a function of shock pressure, infer from thermal expansion, along with a simple parabolic fit and its 95% confidence interval. We see that, in agreement with the simulations, the temperature of the crystals following release always exceeds by some margin the isentropic release temperature at that shock pressure. Interestingly, the temperature of the crystals does not actually increase without limit, but saturates at the ambient melt temperature at shock pressures of around 150 GPa. This happens because the release path cannot easily cross the melt curve owing to the enthalpy barrier it represents. And so the release path will follow the melt curve back towards its zero pressure value. And this, incidentally, we've also verified using MD simulations. But to conclude, the simulations and the experiments are in agreement and suggest that for these micron scale tantalum targets, shock release is a highly non-isentropic process, contrary to the textbook treatment of the process. To summarise then, we've simulated the shock release of micron scale tantalum crystals via molecular dynamics and found that the temperature following release greatly exceeds that expected from an isentropic release. We identified plastic work as being the culprit, which is owed to the high shear strain state the crystal assumes during shock release. And the same excessive release temperature was also observed in laser compressed foils using in situ X-ray diffraction via measurements of the thermally induced elastic strains following shock breakout. So these results show that the assumption of isentropic release that features in many textbooks on shock physics should be treated with caution, particularly if one is dealing with micron scale targets for which the strain rate in the release fan is extremely high. These elevated temperatures assumed by such targets during release necessarily alter its trajectory through phase space, and thus where it might encounter any phase boundaries during unloading, and surely also influences the kinetics of any transitions or reactions that might ensue during release. So with that, I'll thank you for listening, if you have been, and I'll also thank my many collaborators whose names I list here. If you'd like to read more about this study, the letter and accompanying supplemental material may be found at the address provided below. Thank you.